Hi folks, it's Mr. Robeson here. And this one we're going to look at how to make confidence intervals for proportion. So we're just going to look at P first, and then after we do all the P stuff, we'll come back in section 7.3 and we'll do all the stuff for means. All right, so P is population proportion, remember? So we've got a random sample of Skittles. Here's our population. Like it's a big bag filled with tons and tons and tons of Skittles. We actually have these in class. We would be doing this in class, but we're not in class. Sorry. I've actually changed it to beads, but whatever. What's our sample size here? So we took a random sample from this bag. In fact, just about any sample we would close our eyes and take would be a random sample. So if we count how many Skittles we have, so the big ones are 10, there's 6 plus 2, so this would be our sample size here. Our N is 48. What's our P hat? For green. So the proportion that are green are, let's see, that's 10 plus 6, so that'd be 16 out of 48. All right, we can actually divide that if we want, get a decimal, or we can just leave it as 16 out of 48. That's fine. How would you go about creating a confidence interval for P, and what conditions do we need to consider? All right, so we need to have a sampling distribution to make a confidence interval, and we need that sampling distribution to be normal. All right, we need to make sure our sample's not biased, so it needs to be a random sample. And we need all of our samples to be independent for it to actually be a sampling distribution. So we need to make sure our sample size is less than 10% of our population. So here are those conditions right here. So we've got have a random sample, condition number 1. All right, otherwise the p hat could be biased. So we're eliminating bias there. We need to have a normal sampling distribution. And to check for that, since we don't have p, we use p hat. So we usually do n times p. We're going to replace it with p hat since we know p hat and we don't know p. We're trying to figure out p. So we do n times p hat needs to be greater than or equal to 10. We got to check that. And we do n times 1 minus p hat has to be greater than or equal to 10. If both of those are true, then we'll have a normal sampling distribution, or we'd say approximately normal sampling distribution. And the third thing we need, which we generally call independence, is we need our sample to be less than 10% of the population. Otherwise, the samples will not be independent of each other, and we can't use the standard deviation formula that we use for sampling distributions. All right, so these three conditions are sometimes called the random condition, the large counts condition, and the independence condition. All right, but we always have to check all three of them. All right, so the formula here, so if we have a C% confidence interval for an unknown proportion P, it's given by P hat plus or minus Z star, we'll go over that in a second, times the square root of P hat times 1 minus P hat over N. So we've kind of taken the standard deviation formula and we've replaced P with P hat, which actually gives us something slightly different than standard deviation, but it's as close as we can get since we don't know P. And Z star, what is that? Well, that has to do with the number of standard deviations we're going to go over. So Z star is the critical value. So remember critical value we talked about last time, the end of the video? All right, it's the number of standard deviations of the normal curve based on the C% confidence interval. In other words, C% is the area between negative Z star and Z star for the standard normal curve. Remember, the standard normal curve has a mean of 0 and a standard deviation of 1. All right, so we'll see how that works in just a second. So, but first, usually we use P in this standard deviation formula. Usually like the standard deviation of P hat is the square root of P times 1 minus P over N. But since we're using P hat, instead of calling this the standard deviation for the sampling distribution, we call it the standard error, or SE. Or SE, we put a little P hat, so P hat, which tells us we're working with P hats. We have one for means as well. We'll go over that next time. But yeah, this is now called the standard error, SE, instead of standard deviation. All right, it's part of the margin of error. That's why we call it error. It's not because we did something wrong. It's because it's part of our margin of error. And there's Max sleeping on the couch upside down. He does that. All right, so back to our Skittles example. So suppose there were a total of 500 Skittles in the big bag. So that's our population size. That's our capital N for population. Below is the random sample. Remember, we took a random sample of Skittles. So our N here was 48. Our P hat was 16 out of 48. All right, are the conditions met? All All right, so first condition is, did we take a random sample? Well, yeah, it's stated. So we would write random sample stated. And we just go ahead and underline it in the question. But we're saying it's stated here. They give us that information. Normal sampling distribution. Well, we need to do n times p hat. N is 48. P hat is 16 over 48, which is 16. 48 just cancel, which is greater than or equal to 10. That checks out. And we do n times 1 minus p hat. So we have 48 times 1 minus 16 over 48, which would be 48 times, what's it, 32 over 48, which is 32. Notice these two numbers, 32 and 16, they add up to make 48. It's always going to be the case. They always add up to your sample size, which is also greater than or equal to 10. So this means we do have an approximately normal sampling distribution. Yeah, and I do have to write out that whole thing just to make sure I'm getting all my points. Approximately normal sampling distribution, check. Is n less than 10% of the population? So our sample size was 48. Is that less than 10% of 500? Well, 10% of 500 is 50. So yep, that checks out. So we have independent samples. All right, so there's our three conditions. They all work out. All right, so here's an example. If you want to try this on your own first, just pause it, do it on your own. Which condition, if any, does the following scenario fail to meet? Mr. Robeson wants to know the true proportion of red Skittles, the best Skittles, in an average bag of Skittles. He randomly selects, oh good, I'm randomly doing something, a bag of Skittles, which contains 52 Skittles, of which 9 are red. He wants to calculate a 95% confidence interval for the proportion of red Skittles in a bag. So what's the problem here? Is it a non-random sample? Well, no, I said randomly, so that's not it. Is it not a normal sampling distribution? Well, that's work. I got to check a bunch of things for that. Are the samples are not independent? Well, our sample size is 52. Is that less than 10% of all Skittles? Well, if we did 10 times 52, that'd be 520. There's definitely more than 520 Skittles. In existence. There's definitely more of those. So this is not the problem here. Are all conditions met? All right, we'll go back and check the normal one here. So remember it's n times p hat. So n here would be the 52. P hat would be the proportion that are red, which is 9 out of 52, which gives us 9. Is that greater than or equal to 10? No, it definitely isn't. So this is our problem here. So this is our answer. It's not necessarily a normal. It may end up being normal, but we don't know that. It doesn't look like it's going to be big enough to be normal. All right, so that means we can't do any of the work for this guy. We would stop right there and say, not normal, doesn't work. All right, so what happens if condition is violated? So we want random samples of size 20 are selected to create 95% confidence intervals for a population proportion P, where P is 0.25. What condition is not going to be met here? Well, they're giving us P ahead of time, so let's see. They said they're taking random samples, so random is not the problem. All right, what about the normal condition, the large counts? Well, n times P, 20 times 0.25 is, well, 1/4 of 20 is 5, which is not greater than or equal to 10. So that's the condition that's not met. The normal condition. All right, so let's look what happens. So I have a simulator online, so I can set my proportion P to be 0.25. I can set my confidence level to be 95, and I can set my sample size to be anything I want. I set it to be 20. And I did this over and over and over again. All right, so I did all these confidence intervals, projected them. Here's our 0.25 right here. That's our P. And we should capture that 95% of the time. That's our confidence level. But if you look down here, the percent that actually hit it, it's closer to 90%. All right, so that's a problem. It should be 95, and it's only down at 90%, and that's because this normal condition is not met. All right, so that's what happens if one of the conditions isn't met. It doesn't give us what we want. Like we don't get the confidence level that we want. All right, so that's it for the basics here. We'll come back next time and we'll actually do it